So I want to talk to you today about electrons and energy levels in atoms, and just go over the basics of the equations you need to know and the kind of concept behind all this. So you might start off with an electron sat down here at energy level 1. Now this scale is at 10 to the minus 19 joules, so this is negative 6.4 times 10 to the minus 19 joules. You don't need to worry too much about that negative sign, it's just there as convention. And basically says that if you, this is the amount of energy you would require to remove the electron from level 1. This is actually the ionization energy. For those of you that do chemistry, if you supplied 6.4 times 10 to the minus 19 joules, kind of exothermically, then the electron would move up to level 0, where it would be infinitely far away from the atom and therefore would be ionized. But if you supply just a small amount of energy in the form of a photon, then you can raise the electron to the next energy level. So if we bring it up this way, we can raise it so that it comes and lives here at level 2 instead. And we can figure out how much energy is required to do that. We've gone from 6.4 times 10 to the minus 19 joules up to 3.2 times 10 to the minus 19 joules. So that tells me that the energy difference E2 minus E1 is approximately, or exactly, 3.2 times 10 to the minus 19 joules. So that's how much energy is required to jump between 6.4 and 3.2. So where does that energy come from? Well, I said before it comes from a photon, and the energy of a photon is given by E equals hf. E, of course, is the energy of the photon. H is Planck's constant, which is like 6.6 times 10 to the minus 34. And F is the frequency of light that photon would have. So you can quite easily work out now what frequency of light would a photon need to jump this electron from level 1 up to level 2. If you want to calculate that, you can, but it's fairly trivial. All you're going to do is 3.2 times 10 to the minus 19 divided by Planck's constant, 6.6 times 10 to the minus 34. So I guess as an order of magnitude, that's going to come out to be something like 10 to the power 10 to the power 15 hertz, something like that. However, if you had a more energetic photon, then you could take your electron from living down here in level 1, and you could jump it straight up to level 3. So let's do that. This time we get a bit more energy, and this time the electron ends up at level 3. Now if you wanted to do that, you'd need a photon with energy 6.4 minus 2.8. Let's hope my maths doesn't screw up here. 3.6. You'd need 3.6 times 10 to the minus 19 joules, because the difference between 6.4 and 2.8 is 3.6. So again, you could work out the frequency of light needed to jump that electron up. Now, you might think, well, okay, so we had 3.2 here, and then we had 3.6 here. So what about if we had 3.4 joules of energy? Could we do it so that the electron moves from level 1 to part way between level 2 and level 3? And the answer is no. The electron has to go to a very defined energy level. The energy levels are what we call quantized. They can only have specific values. So you cannot use a photon of the wrong frequency to jump the electron up an energy level. Now let's discuss what happens when the electron falls back down. So let's get a down arrow and nice red. So if this electron falls back down, the exact reverse happens. However, instead of the absorption of a photon this time, a photon would be emitted. So the electron jumps down, and an electron is given out in the process, which is pretty cool. Sorry, I said an electron is given out, a photon is given out in the process. And this is how light rays are produced. That leads us on to talk about these different spectra. So of course we've got the continuous spectra of light, and that is all of the different wavelengths of visible light that would be possible to be seen. Then we have two different spectra. We have emission or absorption. Let's talk about absorption first, because that's what we discussed. When these green arrows move the electron upwards, a photon is being absorbed. So it might be that if a photon is absorbed and the electron moves between level 1 and level 2, it's this black line here that represents the photon that did that. So imagine a stream of photons moving through a gas. Some of the photons are absorbed. This photon would be absorbed, the one that corresponds to this energy change. The one that corresponds to 1 to 3 would be absorbed. And the one that corresponds to 1 to 4 would be absorbed. But it doesn't stop there. There are other ones as well. We could have 2 to 3. We could have 3 to 4. So all of these things happen, and that leads to these different absorption lines. These photons never pass through the gas because they were absorbed by the gas. Now we could take the exact opposite. What happens when, and I'm going to need some different colours here, what happens when we have an excited gas? Well, if it's excited, all the electrons are at the higher energy levels, so what are those electrons going to do? Well, they're going to fall back down. That one could fall from there to there. It could fall like that. You could get it falling all the way down like that. It could fall like this. It could fall like this. All of these different falls represent different photons being emitted, and these are the colours you see here. So you don't see any sort of random colours in between those frequencies, you only see discrete frequencies that correspond to one electron transition. This whole concept is really not too difficult. Electrons can only exist at specific levels. When electrons move between levels, they either emit a photon or they absorb a photon. The energy of that photon is given by E equals hf, where h is Planck's constant, f is frequency, and E is the energy of the photon. Hopefully that all makes sense. If you've got any questions about that, or you want to ask anything further, feel free to ask on YouTube or on Edmodo.